Good evening, everybody. Good afternoon. And welcome to webinar number 83, which is all to do with the Earth and the Moon and the Sun and how we use these to determine time. So, excellent topic, quite complicated in places, quite simple in others. So, let's get stuck into this. Quite a bit of my computer is deciding not to go. Right, there we go. So we've got quite a few little bits to this, a little bit longer than last week. We've got to deal with sidereal and synodic time. Those two words will come up quite a lot in this study. We'll have a quick flip through lunar phases. We're just having a chat. A lovely gibbous moon around about 10 a.m. in the. It was almost in the northeast this morning. We'll look at sundials and shadow sticks. I know some of you are very keen to do shadow stick experiments. I know some of you have actually carried out shadow stick experiments to determine longitude, and that's brilliant, and they've been superb. And the equation of time, a very strange concept, and then a little bit about longitude and time zones. Right, so that's the content this afternoon, this evening. And just a reminder that although this is a year 2 webinar, this topic is actually in the material for paper 1. Okay, remember the 2 years of your course in GCSE astronomy have been modified from the original edXL suggestion, really for content and interest and so on, and not to deal with, the difficult things right at the end. Bringing some in a little bit earlier than that. Right, these two important words are sidereal and synodic, which is exactly the same as solar. And it depends if we're talking about with respect to the stars or whether we're talking about the sun. So we're going to have different sidereal days from solar days, and we're going to have different sidereal months from solar or synodic months, or the ones that we see in the sky. Right, so it just mentions that we use atomic clocks now to determine time and so on, but the ideas of time, minutes, seconds, not seconds necessarily, minutes, hours, days, months, and years are all based on astronomical phenomena, obviously, because we're the oldest science. And the best, some would argue. So let's do the easy stuff to start with. There's a diagram straight from the book showing the sun. And what we're going to do here is look at the concept of a year and also a day. So there we are. It's a kind of oblique diagram in a way, with the Earth going around the sun. You'll notice that the axis remains the same. The Earth's axis remains the same. All right, it's tilted. Now, we have different viewpoints here. You can say it's tilted at 66.5 degrees to the ecliptic, or it's tilted at 23.5 degrees to the vertical. So that means if it was straight up, if it was straight vertical on our diagram here. Unfortunately, the Earth does have a tilt. It makes it interesting, actually, gives us seasons and things like that. But 1 year is the time for the Earth to orbit the sun once, to go round the sun exactly once. So it's a solar year, really. That takes 365.25 days and a few seconds, but more or less exactly 365.25 days. So every 4 years, no, I correct myself, almost every 4 years, we have an extra day. And that describes what we mean by a leap year. I don't think leap years are actually mentioned in the spec, but we might see them later on. I think you really ought to know what leap years are. So the year with respect to the sun, the solar year, is really from the spring equinox through the summer solstice and through the autumnal equinox and through the winter solstice that we'll have soon, 3 weeks, and back to the spring equinox as well. So it's the time taken for the sun to be at the first point of Aries, And the first point of Aries again, a few hundred days later. Now, the sidereal day is different from the solar day. The sidereal day is the time it takes the Earth to rotate once, 360 degrees once. 23 hours, 56 minutes. The actual day is 4 minutes longer. And that's because in the time it takes the Earth to spin once, it's actually moved a little bit in its orbit around the sun. And we'll talk more about that as we progress. Right, so what are months? Well, let's just have a look at this. Yes, we don't need that little bit on here. Oh, well, somebody wants a question early on in this. So let's have a look. Let's have a look at an easy question then, just to see what kind of things Edexcel might ask us. Which of the following is the shortest period of time? A leap year. So we ought to be aware of that because it comes in questions sometimes. The sidereal day, the synodic or the solar day, and the synodic month. Well, I don't think it needs too much brain searching to rule out A or D. A year is much longer than a day, and a month is much longer than a day. So they're out. Not A, not D. So it's a choice between B and C. Now, if you remember, the sidereal day is 23 hours and 56 minutes, and the synodic or the solar day is 24 hours exactly. So the shortest period of time, let's hope I put the right letter in. I can see you waiting, and it's answer B, sidereal day. There we go. And that's a nice straightforward question that you could be asked about. So let's get back to these phases of the moon. Now, the moon doesn't give off light by itself. It reflects light from the sun. It can still be out in the daytime. It can still be visible all night long when it's a full moon, but we only see it because it reflects light from the sun. And depending on where, it's a bit like ordinary lighting. You know, if you have a dark room and you have just small lamps at different places, if you move the lamps around, then you can see somebody in the middle of the room from a slightly different viewpoint. You know, if I switch the lights off and in here, and I just had light from the sun coming in, only this side of my face would be lit up, and this side will be in darkness. So we see the different phases of the moon. So all the different appearances of the moon are its phases, basically because it's moving around the Earth and the Earth's moving around the sun. Now, we ought to know about the cycle. So the cycle starts off as what we call a new moon. Now, a new moon can't be seen. It's not visible. It's directly in line between the sun and the Earth. And in fact, it might cause a solar eclipse. And more about that in another module later on. I reckon it needs about 2 or 3 nights later, and this is early evening. The moon can be seen as a very, very thin crescent in the west. So thin, sometimes you miss it. As I say, it takes about 2 or 3 days, perhaps. If you know where to expect it, probably a couple of days. So we're going to have a look at this. The images are from right to left, because the moon is undergoing a kind of left towards the left motion across the sky as far as time on Earth is going. So we see the waxing, that means getting fuller. Crescent, there we are on the right hand side, a very thin crescent, then a slightly larger crescent, and then a half moon. But the middle one, I think you can see quite easily there, the Sea of Crises. On the middle one, the Sea of Crises, the Sea of Rains, the Sea of Serenity, the Sea of Tranquility are all there. So the Sea of Rains is the one at the top, the Sea of Serenity a little lower down, the one towards the bottom is the Sea of Tranquility. You can see a nice contrast near the terminator of the moon. Lovely to observe the moon with binoculars or a small telescope when you have sort of half full or slightly gibbous moon that's slightly more than half full, because you really do near the terminator see amazing contrast. Really looks three-dimensional. You can even see on there, I can make this out, This is a blown up diagram, of course. You can even see the Pennine Mountains and the Alps, I think, as well, further up. We're still heading further away from the sun. So the sun is setting in the west, and we've got the moon at a certain time, say, 7 p.m. or something like that, and it's moving to the left. Its right ascension is increasing. Eventually, it's going to be directly opposite the sun, and we'll get a lovely, well, there's a nice gibbous moon. We're not quite there yet. Look at that. Look at the images there. Wonderful. What's that? Is that Copernicus or Kepler? I can't see the other one. I think that is Kepler. Looks very three-dimensional. The Sea of Rains up towards the top there, and the Ocean of Storms. Wonderful. See Tycho at the bottom there. It's almost lost in the brightness. However, we're not really interested in the detail of the moon. It's just such a nice image, that I think. Quite pleased with that. There's our full moon, and this is 14 days, more or less. The moon is full. It's on the opposite side of the sky from the sun. So from now on, we're going to see the moon more in the morning rather than the evening. So the moon is now waning. Again, these images are moving from right to left. And you can see now that the moon is becoming less full. So basically, the terminator in one lunar month sweeps across the moon, one making it bigger and one making it smaller in terms of the area that you can see. So we have the waxing 14 days and the waning 14 days. There we go. Right. Let's see if we have any questions. No, let's move on. Let's move on. I'm sure that Alistair and Nico will deal with the chat as we go through. Now then, we're getting on to more serious stuff and more complicated stuff now. Sundials and shadow sticks. Before there were clocks, there were sundials and there were shadow sticks to determine time. And both can be used to determine what we call local mean solar time and your longitude. And both use a shadow cast by something opaque, so something that doesn't let light through. So it can be a rod in a plant pot on the left-hand side there, and there's its shadow. Or it can be this wonderful sundial that I found in the Northeast on holiday about 15 years ago now. And I thought, it's such a nice image, I'll use it in the book, and there it is. Not sure where exactly it was now. It might come up later on. It might be in the book, actually. It might give the place there. This thing that casts a shadow has got a very strange name. It's called a gnomon, Gnomon. And the slanting edge must line with the sundial to the north celestial pole. So if you go to the bottom of that sundial in the northeast of England, and you do that at night, it will point to the north celestial pole. Now, it can be really, as long as it's close to Polaris, that, I think, for the purposes of accuracy, will be good enough. But it mustn't be aligned to magnetic north. So you don't use a compass to align your, first of all, with the north, and then secondly, the altitude, which is the altitude of Polaris, which, of course, as you know, is equal to your latitude from webinar number 72, I think, something like that. Now, this gives you, if there's a dial there on a real sundial, I can't actually see any dial on the ground there, but I think it's lost in the pebbles. It might extend further from that, actually. So there will be a scale there on the ground somewhere. And that gives us our apparent solar time. So it's the time that the sun that appears in the sky actually gives us. So that's the time on a sundial. And we've got a few abbreviations here. That's AST, apparent solar time. Now, isn't the time on your watch, by the way? Let's just have a pause of that and just have a look at how we can use a sundial to determine apparent solar time. Well, where is the shadow? Where is the sundial? Sorry, I mean a shadow stick. Let's see how a shadow stick can be used to do that. The sundial can be used to find apparent solar time any time of day as long as the sun's out. But the shadow stick can only determine 12 noon apparent solar time. It can only tell you when it's 12 noon, according to the real sun in the real sky where you are. All right, so apparent solar time is determined by the real sun up there casting shadows in the sky. Sundial can give you any apparent solar time. The shadow stick only gives you 12 noon. So we can work out, we can do an experiment, and we can work out using the fact that the sun is highest in the sky at our apparent solar time of 12 noon. We can use that and our shadow stick, and measuring the length of shadows, we can use that to work out our longitude. Now, full details are in the new pupil toolkit. I'm just going to go briefly over this today. If you want a copy of the details, just send me an email, okay? And I'll send that out to you. If you've got the new pupil toolkit that has the observational skills section, it's in there. Right, let's look at this graph. Now, somebody has started off at 10:40 in the morning. Time along the bottom is time on your watch, what we call Greenwich Mean Time, GMT. Okay? The one that the town hall clock, the one that you phone, the one that, is a clock that we use for civil purposes. This person's started off at 10:40 in the morning and ended up at 1 in the afternoon. And this person has measured the length of the shadow cast by a stick every, looks like 10 minutes, I think. No, I have a fib there. Every 5 minutes, right. And as you can see, as the sun has got higher, as we go on, the shadow length has got lower. That's right. In the summer, when the sun is low and setting, you got a really long shadow, haven't you? Right, so that series of crosses can then be used to draw a line of best fit, which is a lovely smooth curve with no humps and bumps and little jiggly jaggly bits. And we can determine from that the time, GMT, at which the shortest shadow occurs. I reckon from this, although we haven't drawn a line of best fit, I reckon it's 11:50. That's not bad, is it? 11:50. But bear that in mind, 11:50. It might not be. It might be slightly 11:52 or 11:51. Depends on the lovely smooth curve. And you'll notice that I've actually started the length axis at 500 millimeters and gone up to 600 millimeters. Otherwise, you just get a little shallow bowl. You won't get a big dip like we've got here. Now, before we move on, we've got to talk about the other sun in the sky. It's not really there. You can't ever see it. It's imaginary. But there is also a mean sun traveling either in front or behind or occasionally at the same place as the real, what we call the apparent sun. Real and apparent in this context are exactly the same. So you see, the real sun doesn't move across the sky at the same rate every day. Now, we don't notice this. We don't think, wow, look at the sun whizzing across the sky. That doesn't happen. You know, we don't think, oh, the sun's slow today. Oh, look at it. It's hardly risen in an hour. No, we don't notice it at all because it's very, very small. But there is an imaginary sun called the mean sun that travels on the ecliptic at the same speed every day. So it covers the same angle in a given time interval every day throughout the year. The real sun doesn't do that for reasons we'll see shortly. It can be up to about a quarter of an hour ahead or behind the mean sun. And the difference between them is called the equation of time. We've got this lovely graph, a big dipper and a little hump and a little hump, a little dip and a big hump. And this is the equation of time in minutes. And as you can see, it varies throughout the year. This weird graph is the result of the superposition of two simpler graphs. And sometimes they reinforce each other and sometimes they don't. So by the fact that the sun is fast means that the real sun in the sky is so many minutes in front of the mean sun. So the mean sun is lagging behind. And that occurs early on in the year up to mid-April. Then the real sun gets a bit faster. So it moves across the sky at a faster rate. So it's ahead of the mean sun. And then for a couple of months, it's behind again. And then it's way ahead from September to December. Okay, so I won't go into the reasons just now, but the mean sun is the one that just ticks along the ecliptic. We are. Oh, you can't see that, can you? I'm thinking you can see what I'm doing. If you look on the front cover of the book, you'll see that the real sun goes sort of up to the summer solstice and crosses the uh, right ascension axis at the first point of Libra, and so on. The real sun does that. The mean sun goes along the ecliptic. Right, let's move on. Now, the difference between the equation of time is this correction. It converts apparent solar time into mean solar time. And here is the formula. So I'll just say again and explain these abbreviations. Once local apparent solar time has been determined, you have to convert it to mean solar time. So you do that by using the equation of time. Really, it's a correction factor. So you look at the time on a sundial, you apply the equation of time, and it gives you the mean solar time. So the equation of time is actually the apparent solar time, take away the mean solar time. And what I've done is rearrange that. So just a bit of algebra. So the mean solar time, where you are locally, is the apparent solar time, take away the equation of time. Now, if you know your longitude, you can convert your local mean solar time into the mean solar time at Greenwich. So for every degree west you are, you add on, for every degree west you are, you take away 4 minutes. And if you know your local mean solar time in Greenwich, compared with your mean solar time, you can work out your longitude. We'll look at examples of this a bit later on. So to find your longitude, let's just summarize. You use a shadow stick, and you realize that the apparent solar time is 12 noon when it's the shortest shadow. You've got to convert that into mean solar time where you are. So you apply the equation of time, you add on or subtract the number of minutes, and that gives you local mean solar time. Now, if you convert that, if you look at the difference between that and Greenwich mean solar time, so say Greenwich mean solar time is 12 noon. So on your watch where the shortest shadow was, that says 12 noon. I'm just using 12 noon as a nice example here. All right. So if you know that your local mean solar time is 12 noon, but you know in Greenwich, the real time, so on your watch, on your clock, is 12:06. 6 minutes difference corresponds to, remember, 4 minutes for 1 degree. That corresponds to 1.5 degrees. So you'll be 1.5 degrees east or west of Greenwich. And because your local mean time is behind Greenwich mean time, you will be further west. Just taking an extreme example, if you're in the United States, you'll be 5 hours, 6 hours behind Greenwich Mean Time. Right. Whew, this is not too easy. This needs looking at with pencil and paper, I think, as well as on a screen. So there we are. So local mean times, when it's 12 noon in Greenwich, somewhere between Calais and Dunkirk is 12:08. Bournemouth is 11:52, so that must be 2 degrees west. Notice 8 minutes difference. Plymouth, we've got 11:44, and on a boat to the Scilly Isles, the local mean time is 11:36. So we must be, let's see, 11:36 is 24 minutes. 24 minutes. And 24 minutes corresponds to 6 degrees. So basically, if you know your local mean time and you know local mean time in Greenwich, you can find your longitude. And that's how the longitude problem was worked out. The longitude problem was the problem that sailors and navigators in the sort of 17th century and so on didn't know where they were in terms of longitude. So remember, please, that the Earth rotates by 1 degree every 4 minutes. Okay, it's slightly under 4 minutes, I know, but sometimes we have to be fussy with this 23 hours, 56 minutes sidereal rotation period, the sidereal day. Sometimes we don't worry too much about it because the difference is so small. So when we're talking about the Earth rotating by 1 degree as opposed to 365 degrees, doesn't really matter. You know, a minuscule few seconds doesn't really make that world of difference. Not at GCSE level. Right, a new teacher, and we've got a new class of really interested students here. And the teacher is suggesting, no doubt they've been asking, let's have a look at some past paper questions on shadow sticks and sundials. Right, okay. An astronomer on board a ship took measurements of the sun to measure the ship's latitude. They actually mean to determine the ship's latitude. You only measure things with a measuring instrument. And there's no device called a latitudometer yet. It's not been invented. So we've got the time, rather like that graph we've seen a few minutes ago, and there's the altitude of the sun. So instead of the length of a shadow, they've just worked out the altitude of the sun using a clinometer or something like that. There we go. So nice, regular, every 15 minutes. Not terribly good. I'd have done it every 5 minutes, something like that, I think. And let's have a look at this. The astronomer also looked up the declination of the sun, which was 8 degrees, we presume plus 8 degrees. And the astronomer used these measurements to make the following. The sun is at 42 degrees when it's at its highest point. This means that latitude is 42 degrees, take away 8, so 34 degrees. Looks convincing, but I don't think it is. What we've got to do is to plot a graph of the measurements. I've not done that. And estimate the accuracy of the astronomer's value for a ship's latitude based on the observational procedures. 6 marks. 6 marks. We've got to look at let's have a look. We've got to evaluate the accuracy. So is it an accurate result? If so, why? What have we done? What has he done right? Or she done right? If it's wrong, then we've got to look at the inadequacies. And lots of things to go in here. Right. Here is straight from the specification. So it's good that the readings are taken either side of local known. You've got to state the obvious sometimes in these. Measurements taken on whole numbers of minutes, that makes it easy to plot. But the intervals in readings, oh yeah, I mentioned this, didn't I, are too large. Every 15 minutes is not good enough. Very difficult to know where the bottom of the graph is. Around noon, the sun is moving 1 or 2 degrees between readings. I'm not quite sure what that is getting at. An error of 1 degree in latitude represents a distance of about 70 miles. The altitude of the sun at noon is correctly assessed from the data, 42 degrees, but the latitude calculation is incorrect. So that is not using the correct formula. And we'll look at that in another question later on that shows a solar analemma. Explain what they are shortly. Right, so that's the kind of content in these 6 markers that you have to you should write everything you know about what they're asking. Good points and bad points. Difficult to observe the sun, the height of the sun from a rolling ship, isn't it? I'm sure. Right, let's look at this equation of time and explore this in a bit more detail. So what we've said here is that the sun in the sky, so the apparent sun, and the mean sun that doesn't really exist, but as a concept it does, they only actually agree on 4 dates of the year. The equation of time then is 0. That's quite nice to do an experiment to determine longitude when the equation of time is 0, because you don't need to worry about it. But then as a challenge, you might like to do your experiment when the equation of time is not 0. Excuse me. In between, the sun can be fast or slow. Now, there are 2 reasons for this, and you're often asked about this. We said we'd come on to this later, and the later is now. First of all, the moon orbits the sun in an ellipse. So the Earth moves at different speeds with respect to the sun. So sometimes the Earth's a little bit ahead in its real orbit compared with if it was going in a circle. and sometimes a little further behind. It's a little bit like libration in longitude with our friend the moon, librations. And the other thing is that the Earth's axis of rotation is tilted to the ecliptic. So basically, the sun has to follow this kind of little sine wave, if you know what a sine wave is. That graph that's on the front of the textbook, again, the graph showing the right ascension of the sun, the declination. The sun, the real sun, doesn't move across the ecliptic. The mean sun does, but the sun has to go further north and then come back down to the equator and then go south and to the equator, and this takes a longer time. So the doubling, the combined factor of these two little anomalies gives rise to the equation of time, the fact that the real sun and the mean sun don't move across the sky together. Now, you ought to be aware, so we'll mention this here, that the fact that the Earth is tilted is actually called the obliquity of the ecliptic. So it's the elliptical orbit of the Earth and the obliquity of the ecliptic. Be careful, we've got elliptical and ecliptic. We've got some very close together words there that mean very different things. So that is why, we're not going to go into any more detail about that. That is why we have this discrepancy between the mean sun that ticks, a clock that ticks at the same rate every day, and the actual sun in the sky that speeds up and slows down. And there are your two reasons. In fact, the moon's not axis of rotation, but actual path taken with regard to the ecliptic. So it's something to do with tilt as well that gives us that other libration in latitude. Right, let's move on. Lots to do today. Another keen lot of students, very young students here, younger than some of you, I think, and the teacher's going to ask, oh no, it's somebody else. Please, miss, can we see some past paper questions on the equation of time? Of course, sure. So, Caitlin, very bright student asking this. I think some of you have gathered that these aren't all astronomy students. I've just used something from the internet that's copyright free, but we can pretend that they are. Right, now then, this is from a few years ago. There were 4 questions all in a row, and I think they got them in the wrong order. But anyway, let's have a look at this. A sundial in the United Kingdom shows 11:15 a.m. on a day when the equation of time is minus 6 minutes. So we've got, let's work through this. Let me get... You can see the correct running order. Right, that's important, not just at the moment. Right. So, nope, up to you. Right, so the sundial's longitude is 3 degrees west. Right, we're going to be asked all sorts of things here. This is very important. This comes up a lot. So we've got the sundial. So AST is 11:15 a.m. Okay. The equation of time is minus 6 minutes. So we can work out mean solar time. So the equation of time is AST take away MST. I don't really like using these abbreviations, but MST is therefore AST take away the equation of time. So there's a little bit of algebra. So the mean solar time is the apparent solar time, take away the equation of time. Right, so the mean solar time is 11:15, take away minus 6 minutes. Oh, so we've got to add it on. So that's 11:15 plus 6 minutes, 11:21. Right, so that's our local mean solar time. And the sundial's longitude is 3 degrees west. Now, 3 degrees corresponds to 12 minutes. 3 degrees, 12 minutes. Don't think that's right. 3 degrees can't be 12 minutes. I always get this the wrong way around. 1 degree in 4 minutes. The 3 degrees in 12 minutes. Yeah, that's right, isn't it? Well, we'll soon see if we're wrong. We are west, and therefore mean solar time is ahead of ours. So our local mean solar time is therefore 11:09. I'm not sure about this. Right, so let's have a look. A sundial. Right, so a sundial at this location. Oh, no, a clock at the sundial's location. So we're looking at mean solar time. So I rate this 11:21, B. What have we done here? Oh, I need to add on the 12 minutes, not take it away. 11:33. Sorry about that, everybody. So the answer is D. Now, a clock and the sundial. So let's just check that I've done this right on pencil. MST is AST minus equation of time. So the mean solar time is 11:15 minus 6 minutes, which gives us 11:21. 3 degrees west is 12 minutes. So yes, we have to add on the 12 degrees because Greenwich is we are west of Greenwich, so our clock hasn't caught up yet. So 11:33. The answer is D. Greenwich Mean Time is the same as a clock time, so we're expecting D again. There we go. Now, the other questions said, what's local mean time at the sundial location? Local mean solar time is 11:21. We've worked out B. Now, don't you have to do that before you work out the time in Greenwich? Don't you think that this has been done? I know I grumble about the exam papers, but it's only so that we can try and get fair questions for students. The apparent solar time is, of course, 11:15. So that's an easy one. That's the key of A. I think it should have been dotty 4, dotty 3, dotty 1, dotty 2 in that order. Right. Explain one of the causes of the equation of time. Well, you can refer to either the Earth's elliptical orbit and varying speed. All right. So if you're going up the motorway in a car and there's a car next to you, and you're both going at the same speed, then all is well. If you put the accelerator down a little bit and go faster, you'll move away. You'll leave the other car behind. If you apply the brakes, the other car will kind of move ahead of you. And you can think of the equation of time a little bit like that. Only there's two factors. It's not quite as simple as I've tried to make out. And one of the factors is the Earth's elliptical orbit. And the other one is the obliquity of the ecliptic. All right. So one of those would give you 1 mark. And then what we want is a reason for the other mark. I've not put that in. We've got this lovely image now of a stone circle at Callanish in Scotland. And what they've done is to take an image of the sun at noon every week. It's an image of the sun, of course, so that's fine. And a little bit overexposed at the bottom. You see this shape of this graph, I call it a wobbly snowman, but the correct name is an analemma. I think it's ANALEMMA. See if there's one in the textbook. Just we look here. Yes, it's on page 44, underneath the graph that we saw earlier. So on page 44, it looks more like a wobbly snowman there. It's wider than the one that we've got on there. Again, it's showing that the sun is sometimes higher in the sky and sometimes it's further sort of east and further west on certain days. Say the approximate date when the image of the sun at the top of the pattern was taken. Now, this is not really part of our topic here, but we need it for subsequent parts, so that's why I've left it in. Do you agree that when the sun is highest in the sky during a year, then it's at the summer solstice, and the approximate date is June 21st? Sun has its greatest altitude, doesn't it? On or around June the 21st. They were quite lenient. They gave you about 3 or 4 days either side in the mark scheme. June 21st. The sun is at greatest altitude. Right, we'll see what that is soon. The solar images form a figure of 8 pattern. I wish they'd say a wobbly snowman. Explain why the pattern appears to have this shape. Well, again, it's representing the equation of time. You can see little dip, big dip, big hump, little hump, can't you? If you turn it sideways, you've got and unravel it, you've got basically this equation of time I showed you earlier. So we've got to either talk in terms of the Earth's elliptical orbit again, or, no, sorry, and it's not really asking all that great detail, and the tilt of the polar axis. Now, I think really, in fairness, you'd need a little bit more than that, but the specification didn't really want you to elaborate. So it's almost a state why the pattern appears. Really, for an explanation, you have to give reasons. So the Earth speeds up and slows down in its orbit, and the fact that the Earth has to follow the ecliptic and not the celestial equator. So it has to go in this up-down shape from the front of the textbook as opposed to straight across. Okay. Point X. Oh, this is a hard one. At the top of the pattern is at an altitude of 55¼ degrees. I don't know why we have to bother about the quarter. I can see the half because it's a true value. But there we are. The altitude of point X is at 55¼ degrees. We've got to calculate the latitude of the Callanish stone circle. Now, this is not really, again, in this option, but this is in paper 1, like this topic. So I thought it'll be useful to put in because it is about the equation of time. You may remember a long time ago, we came to the formula that if we're looking in the south, the altitude of a star is 90 degrees, take away the zenith distance. And the zenith distance was latitude, take away declination. This is not a formula you'll be given. This is a formula you must know. There will be a lot of marks on applying this formula. So this is in the south. It's not the circumpolar stars in the north. This is the webinar we had on coordinate systems. The altitude of a star, like the sun, is 90 degrees, take away latitude, take away declination. Now, we know the declination of the sun at summer solstice, it's 23½ degrees. And we're told the altitude is 55¼ degrees. So we know the altitude at the beginning of our equation. We know 90 degrees. We don't know the latitude. That's what we've got to find out. And we know the declination. So if you make declination the subject, and you've got to remove the bracket first, so altitude equals 90, take away latitude plus declination, because a minus and a minus make a plus again, all right? Rearrange it, you get declination is 90 minus latitude minus altitude. And if you put the numbers in, you get 58¼ degrees, which we assume is north. I think that was the hardest question on the paper last. So altitude, however you remember this, is 90, take away latitude, take away declination. That's in a bracket because it's the difference in basically declination between your latitude, take away the declination of the star is equal to the zenith distance. Of course, altitude is 90 degrees take away the zenith distance. We did prove that at the time. So rearranging it and substituting, I've not done every single line there, gives you 58¼ degrees. That is the correct latitude of the Callanish stone circle. Right, another 6 marker. An observer wishes to make some measurements of the size. Again, you can't measure the equation of time. An observer wishes to use measurements to determine the size of the equation of time to show how it changes during the year. Design a suitable observing procedure. So one thing, every month, on the 1st of every month, I'm going to do this from January through to January. All right? I'm going to do it from a place where blah, 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 blah. I can see the sun, there aren't any trees blocking things. If I can't observe on the 1st, I'm going to observe on the 2nd. So already by considering when and where from you're going to make some observations, you've already got a couple of marks. What we've got to do is to work out the equation of time. So you'll need to know this time your longitude, and you'll need to know the apparent solar time at noon. So you can do this to use a shadow stick and just work it backwards through what we talked about earlier. Right. And in fact, it said in the syllabus, and I've just put this bit in. I've not put the whole shopping list of things you could write on this one, because you might like to try this yourself and send it in to me, and I'll give you some marks. Marks rewarded according to whether the observing program is simple, sound, or detailed. There you go. So I'm going to use the shadow stick and measure the time at which the sun is lowest in the sky, and use my longitude to work out the equation of time. And I'll do this for every day, every month of the year. You might get 2 marks. It needs a little bit more detail. It needs a far more serious attempt at what you're actually going to do. So you'll need to state what the equation of time is. So that will kind of take you into the sound, pretty sound bracket. But obviously a bit more detail. I'm going to observe every 2 weeks so that I'll get a more accurate set of lines to be able to draw my equation of time. Quite a lot going on here. Oh, apologies. I did leave it in. I thought I'd taken it out. I'll let you have a read of that. These are just some of the ideas. I can think of quite a few more. There's nothing about where from. There's the safety bit, needing to ensure no direct viewing of the sun. Nobody in their right mind would look directly at the sun. That's why we use a shadow. So I would elaborate quite a lot on bullet point 2 there. The apparent solar time can be found using a sundial or a shadow stick. I think a little bit more there. The effect of longitude on not the apparent solar time, the effect of longitude on the mean solar time actually needs to be allowed for. So you know the apparent solar time is 12 noon. Full stop. So the equation of time is that take away the mean solar time. So you need to apply the effective longitude on mean solar time. I thought I was being quite nice to the examiners today. So let's finally, in this very interesting, fascinating, this is where astronomy came from, really, the need to navigate. So we need coordinate systems and blah, 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 blah. Got 2 images here from, I think these are in the National Maritime Museum. Yeah, they are in Greenwich. We're an island nation here in the British Isles, and to trade with our neighbours and not so close neighbours, we needed ships to sail all over the world. And it's quite easy to find latitude, as we found out earlier with that question that we had a brief look at, but very, very difficult to determine longitude because it wasn't known the time in the home port from where the ship was sailing. So Charles II, the king, proposed to have this royal committee what it was called now, to determine longitude, to solve the longitude problem. Where are we? What is our longitude? How do we know? So he set up this, what would we call it these days? Sort of action committee, task force, something like that, to determine the time in the ship's home port. There's some images I took there at the Greenwich Observatory. Somebody there in the middle standing, the photographer isn't, but one there is standing with one foot in the west and one in the east, because the line actually runs through what we call the transit telescope. So a telescope that followed stars as they crossed the meridian in the south. So another transit, but we don't call that upper and lower because there's only one. There's the time ball that drops at 1 p.m. every afternoon. So there were basically two attempts at determining longitude. One was called the lunar distance method. So they set this competition up. The prize was about, in today's money, it was about £1 million, dollars, euros, something like that. It was substantial. And what they had to do there was to compare where the moon was in the ship with the known position of the moon from the home port. So they had to do lots of maps and charts, working out what the phase of the moon was and so on in the home port. And then they can compare that with the sort of phase of the moon and the position of the moon in the sky where they were. But unfortunately, there weren't the right charts and instruments to make accurate measurements of the sky. So the longitude problem was eventually solved by John Harrison, who made clocks, basically. And he made, after several attempts, a clock called the marine chronometer. And this, I think, is still, it was missing. I think it was being, not repaired. I don't think these things need repairing. It was being serviced, I think, when I was there a few years ago. And this keeps time. It doesn't matter how much the temperature changes, doesn't matter how salty the water gets, what the humidity is, all these kind of physical factors that might affect how, you know, a sort of clock that's made of springs or a simple pendulum or something like that, that might, you know, go ahead a little bit or fall behind. We want a clock that ticks perfectly accurately and is portable on a ship. So this was like a large pocket watch, about 4 or 5 inches wide, I think, something like that. And Harrison, after quite a bit of debate and struggle, was awarded the prize. A committee of sort of, you know, the king and his minions. So that's really how the Greenwich Observatory got set up. It's a wonderful place to go and visit, and the Maritime Museum as well. Wonderful in Greenwich. So if you know local time on a ship, which you can by observing the sun and the stars, if you know the local time in the ship's home port, you do, because you've got this watch, this chronometer, then you can work out the difference in time that corresponds to 1 degree of longitude. So we've got some sailors on here. One is saying it's 7 o'clock in the evening here. Another one is saying it's 10 o'clock in our home port. And so somebody has worked out 3 hours difference. Our longitude is 45 degrees west. Because if 4 minutes corresponds to 1 degree, 1 hour corresponds to 15 degrees of longitude. I'll just use nice simple numbers there. I don't think you'll get something quite so simple in the exam. Nice and easy one. As I say, some of the questions are quite straightforward, no trickery. Which of the following measurements must be taken in the lunar distance method? And what we've got here, I think, if I'm reading it correctly, and you know, we're looking at exam technique through all this. I know one or two of you have been asking about that. So it's always useful to think, oh, no, that's wrong. So let's have a look. The angular distance across the moon's disk, no, that's half a degree. That's not anything to do with it. The angular distance between the moon and certain bright stars, That looks possible. Lunar distance method is a bit of a giveaway. The angular distance between the moon and the horizon. No, we're not worried about how high the moon is, what its altitude is. And the moon and the comet, I think they were really struggling for option D there. So it's B. There we go. They asked also what's the name of the clockmaker that eventually solved the longitude problem, and they only wanted the family name, the surname. So it's John Harrison. Give you the John there, Harrison. Okay. Oh, and we haven't really spoken about time zones, but the Earth's surface is split up into a whole number of time zones, approximately 15 degrees wide. And it's so that really we can all have the same time. In a time zone, we all work on the same time. Work on the sun, you know, there's quite a few minutes difference. So we all have the same time. So people in, say, the very southwest, near what did we have earlier? Penzance and the Scilly Isles, and people who are in the very northeast, so up Aberdeen, Inverness, that kind of way, even the Shetland Islands and so on, they can all use the same clock. So it's the same time everywhere in that time zone. If not, we can't synchronize our watches. If it's difficult to work out what time a train will arrive at a station if it's a long way east and a long way west. And of course, we also have time zones that alter their time. So they're 1 hour apart, most of the time anyway, 1 hour apart. So that effectively, all different people in the world at noon, at 12 o'clock noon, are in sunshine. And at midnight, they're all in darkness. And they also get up at the same local time, according to the time zone, as their clock shows. So everybody gets up. I know there's exceptions, but everyone gets up at sort of 7 o'clock, 8 o'clock in the morning, and it's just getting light at the moment. Now, if we didn't have time zones, it might be just sunset at 7 a.m. this morning. We couldn't keep up with the changing seasons. And yeah, if the Earth's surface is divided into 24 time zones, 360 degrees divided by 24, I think is 15. Don't know if I've got any answers here. Yeah, here we are. And I think a final question. We've got Alice in London and Bob in a European city. And we've got some dates here. Time of sunrise, time of sun, oh yeah, and day length. And Bob, time of sunrise and day length. And we've got to analyse this table. It does need a bit of analysis, actually. Is Bob east or west of London? And is Bob north or south of London? Analyse table 2 to determine the location of Bob, east or west of London. Well, the sunrise on any date is earlier, isn't it? So I would say that Bob is west of London. Let's have a look to see if I'm right. I'm doing these. Oh, east of London. What? Oh, yes, it's earlier. Oh, it's GMT. It's GMT. Yes, not local time. This needs a bit of sorting out, I think. Why is Bob south of London? Probably because the day length is longer and sunrise occurs earlier. Yeah. Bob is south of London because the change or range of day lengths from February to May is smaller compared with London. I'll have to have a different study of this, I think. This really does need a lot of analysis. So we're dealing with the spring, winter and spring, Feb, March, April, and May. So as we go down. So Bob is south of London because the rate or the change of day length from February to May is small compared with London. So I suppose Bob is nearer the equator, for which the length of the day and so on, and the difference between sunrise and sunset is less noticeable. Yeah. That's the kind of question. If I was doing that in the exam, I would leave that until the end. when all right, I'll be slightly more tired, but I would address it later. And the second time of looking at it, you think, oh yeah, of course. So Bob's east of London. Let's just have a look, just make sure. Bob is east of London. Your sunrise occurs earlier than in London. Yeah, sunrise is GMT. So if GMT is earlier, yeah, London is further west, and therefore Bob is further east. Yeah, it's just a viewpoint. Sorry, just me being a bit slow there. Yeah, if further, so the sunrise is sunrise in Bob's city is earlier than sunrise in London, and therefore,
sorry, Nigel.
yeah, help me out.
The way I'm thinking of is that the sun is moving from east to west. So if it gets there 2 hours earlier, then it's got to be more to the east because that's where the sun is coming from. So
yeah,
does that make sense?
yeah. So Bobby's east.
I think that's the easiest way to look for me.
Yeah, absolutely. Thank you. I needed a bit of help there. That's very kind of you. Thank you.
Okay.
Thank you. Checks in the post. Right, everybody. Well, let's brought this to an end. So if you've any more questions, I've not looked in the chat just yet, then I will do in a moment or two. And I hope you've enjoyed that. Quite a variety this afternoon. Evening now, isn't it? And next month, we'll be looking at the formation of planetary systems, tidal heating, why some planets or why some moons have atmospheres, why some planets have substantial atmospheres, how we can find exoplanets. So quite a lot. Why have we got 4 terrestrial planets made of rock and iron? And then we have 4 gas giants made of hydrogen, helium, methane, and ammonia, with plenty moons and rings. Why is this great difference? So we'll be looking at the formation of our solar system and thinking a little bit about the history of this. It's one of my favorite topics, I think, planetary systems. So I'm looking forward to getting that all ready and to seeing you in, let's think about it, June. No, June, what am I talking about? See you in December.